Hey mathletes, so today we're going to look at graphical behavior. So what is happening in a graph that might be interesting? So if we look at this polynomial function, we'll notice a few things. We notice that it's got a point down here, it's got a high point here, it's got a low point here. Here we might notice that it hits the x-axis. Okay, we're going to talk about some different things. So one thing we want to talk about is maxima and minima. So a minimum is a low point. It's going down before it gets to the point, and then it's going up after that point. So here, this is called a local minimum. This is called a global minimum. This is called a local because in the area around it, it's the lowest point. So we're going to say this is about where x is approximately 4.25. So that is a local minimum. Over here, we're going to say this is where x is approximately negative 2.5. That is the global minimum. That is the lowest the entire graph goes. As far as maximums go, right here, where x equals 2, we have a local maximum. Everything before it is going up, and then after that it's going down. So it's a high point in the graph. The global maximum is infinity, because this arrow means it goes up to infinity. That means that goes up to infinity. So other points of interest on a graph is where it crosses the x-axis. So we have three places where it crosses the x-axis. These are called roots or zeros. So you would say the roots are where x equals the little set bracket, negative 3, 2, and 5. Okay, the way you know something hits the x-axis, as you can see it actually crosses, this is where y would equal 0. So this is how we solve polynomial functions, or any function, where it crosses the x-axis. We set y equal to 0, and then we solve the equation. Another thing we want to look at with a graph is where it's positive or where it's negative. In this case, it's positive from negative infinity up to negative 3. And also from 5 up to infinity. So you would say the graph is positive. We would use our notation here, negative infinity to negative 3. It's a parenthesis at negative 3 because it's not positive negative 3, it's 0. And also from 5 up to positive infinity. The places it's negative is every place else except 2. It's not negative at 2, it's 0 again. So we would say the graph is negative from negative 3 to 2, and from 2 to 5. Another thing we're going to look at when we look at a graph is the concavity. Concavity is just the shape. So this is a nonlinear function, so it's got a curve. This curve, we call this concave up. Up like a cup. This is concave up. Here, it's concave down, or down like a frown. These points, where it changes from up to down or down to up, are called inflection points. So this thing is concave up from negative infinity to about 1/3, down from 1/3 to say 3.2, then concave up again from 3.2 up to positive infinity. So some graphs, some functions have things called asymptotes. So an asymptote is an invisible line that the graph does not cross. It could be horizontal like this one, or it could be vertical, or it could be diagonal. So in this case, population, real world population, always has an asymptote. So theoretically, without limits, population would just grow forever. We all know that we can't fit an infinite number of people on the planet, or an infinite number of animals in some biome, or an infinite number of bacteria in a petri dish. It's not big enough. There's not enough resources. So what happens is a graph will grow slowly, the population. Say we have a few people, they start to make babies, the population grows slowly, you got a lot more people, it grows faster and faster, but then say you run out of food or space, and that goes slower and slower. This asymptote is a line it will never cross. So as x approaches infinity, the asymptote here, the line it's not going to cross, looks like it's about 190. So the population, whatever this is, cannot get past 190. Either there's not enough space, or there's not enough food, or there's not enough resources. So a graph like this, we have line segments, right? This is a piecewise function. It's made up of these different pieces. And what these pieces mean depends on what the x and the y axis are labeled. So in this case, we have the y is distance from water in feet, and the x-axis is time. So the independent variable is almost always time. It is never dependent on something else. So we can see what's happening here. From time 0 to time 2, somebody is moving away from the water. Say they're walking away from the water, there's a shark. So they're walking away, and at 2 seconds, they get 2 feet away. So they're moving at 1 foot per second. But here, this horizontal piece, if your distance isn't changing, that means we're moving at 0 feet per second. You're not moving. You're just standing there, looking at the shark in the water. Second number 4, the second, say, 8.5, this line is steeper than this line. Every 1 second, it's increasing by 2 feet. So say you see the shark getting closer to the water, you start running faster. So from time 4 to time, say, 8.5, you are moving faster than you were from time 0 to 2. And then up here at the top, from say time 8.5 all the way to time 12, you're not moving again. You have stopped. The line is horizontal, it has a slope of 0, so your speed is 0. And we can see that the total distance traveled is 11 feet. So in the first 2 seconds, you went 2 feet. The next 2 seconds, you didn't go anywhere. And then suddenly you went 9 feet in 4.5 seconds. So places the line is steepest means your y is changing fastest. So in this case, it is distance is changing fastest. If it was going down, we would say you walk back toward the water. When it is flat, it means you are not moving, or whatever the y is, isn't changing. So in this case, you are not walking away from the water, you're standing still. The steeper the line, the faster the y is changing. Flat line, the y is not changing at all.